All right, so today our objective is that we're going to review the real number system, and then by the end of this, you should know more about the difference between rational and irrational numbers. So if you recall, this was actually a standard from quarter one. This week and next week, we're going to look back at some of those standards that we didn't do so great at, that maybe we need to spend some more practice or get some more guidance on them. So today we're going to talk about the real number system and the difference between rational and irrational numbers, because that was one of the things that we had a lot of issues with. We were mixing up our rational and our irrational numbers. So, and if you haven't already, these notes are on Schoology. You can go ahead and print out the guided notes and fill them in as we go. If you don't have a printer, that's fine. Just make sure you include the important parts, so especially this, in our examples, and submit them for an easy grade that shows that you are following along and know what we're doing. All right, so rational versus irrational numbers. A rational number are numbers that can be written as fractions or decimals. Rational numbers include terminating decimals as well as repeating decimals, because we know that if I have 0.2 repeating, we know that for every number we have repeating, we put that many nines under it. So 2 repeating can be written as 2 over 9. So we can write repeating decimals as fractions, which is why they're rational. The square root of perfect squares are also rational. So a lot of times I would see on our homework, we had the square root of 144, and as soon as you saw the square root, you said that's irrational, but the square root of 144 is 12. And we know 12 is a rational number. Irrational numbers cannot be written in fraction form. Irrational numbers include non-terminating and non-repeating decimal, the square root of non-perfect squares. So if this was the square root of 146, it'd be irrational because that is not a perfect square. There's no single number that multiplies to give me by itself to give me that number. All right, so let's look at a couple of examples. So I'm going to go through this with you, and I'm going to ask you to respond and think as to what you think this is as we go. So the first one I see is negative 12. Do you think that's rational or irrational? Why do you think that? All right, so if you said that negative 12 was rational, you are right. Why is negative 12 rational? Did you say because it can be written as a fraction? It can be written as a fraction. And I'm just going to be can be written as, and I'm going to write the fraction, negative 12 over 1. Awesome. All right, so this one should be easy. Do you think that pi is rational or irrational? Awesome, awesome. Why? All right, so you are right if you said pi is irrational, because it is a non-terminating decimal. Awesome. All right, so 0.6, is that rational or irrational? Why? Well, that's exactly right. It's rational. If you said rational, you're right. Did you say why? Because you can say that either that it's a terminating decimal, because we know those are rational. One of our reasons is that it's a terminating decimal. Or you could even say that it can be written as a fraction, because we know if I read it, that's 6/10. So 6 over 10, 6/10. Or 2/5 if we were to go ahead and simplify it. How about 7/8? Is that rational or irrational? Why? All right, so if you said that it was rational, you are correct. And why did you say it was rational? Awesome. So if you put that it can be written as a fraction, because we already said that before, you are correct. Can be written as a fraction because it's already in fraction form. So if we see a fraction, we know it's as, instead of just fraction, fraction. All right, I have 1, 2, 3, 4, 5, 6, dot, 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 dot. Is that rational or irrational? Why? Awesome. So if you saw these ellipses, those should have given you somewhat of a clue. We see those dot, dot, dot. We know this is going to go on indefinitely. We don't know how far it's going. We don't know if it's going to repeat. We don't know what it is. So because of that is irrational. It's non-terminating, and we don't have a line to show me that that's going to repeat. So it's non-terminating, and it's not repeating. Perfect. So this next one, do you think it's going to be rational or irrational? Why? Awesome. This one is rational. You could say one of two things. You could either say that it's a repeating decimal, or that it can be written as a fraction. Because a repeating, and I'm just going to give you the fraction. So you could put or written as a fraction. I just ran out of room. Or, and I'm just going to give you the fraction. We know there are two repeating digits. So we're going to say that's 33 over 99. Or you could say 3 over 9. Because the 3 is repeating, so you could drop the second 3. Which 33 over 99 simplifies to 3/9. All right, how about this next one? I have the square root of 20. Is that rational or irrational? Think about, is there a number that multiplies to give me 20 by itself? No, so you're right. It's irrational. Because there is no number that will multiply to give me the square root of 20. So it is a non-perfect square. Let's look at a couple other examples. I just have the two more. I have negative 1.75. Does that decimal end? Think about that. A lot of people, for some reason, you saw these negative numbers and it threw you for a loop. It's a terminating decimal, and it could be written as 1 75/100, which simplifies to 1 3/4. So it's a terminating decimal. Or it can be written as a fraction, as I just showed you. Because of that, it is rational. All right, how about this next one? Remember, it's a square root. This is where you determine, is that a perfect square? If yes, it's rational. If no, it's irrational. Is there a number that multiplies by itself to give me 121? There sure is. 11 times 11 gives me 121. So I can pull that out and say that it's negative 11. Because that's a perfect square, it's rational. And that would be our explanation. It is a perfect. And that should be a good glimpse at the kinds of examples we might see. These seem to be some of the ones that are throwing us off. Non-perfect squares versus perfect squares. This is an ending decimal, so I can automatically say it's rational. This one definitely threw us for a loop before. Make sure those repeating numbers, you can put them over a 9 and make them a fraction, so it's definitely going to be rational. These ones we all seem to get. This number doesn't end, so it's irrational. 7/8 already written as a fraction, and that is one of the factors of a rational number, so rational. This is already a decimal. Decimals can easily be turned into a fraction, so obviously it's rational. Pi is the most common irrational number. So 9 times out of 10, you guys get that right. And this is just a regular negative 12. It can be written as 12 over 1, so it can be written as a fraction, right? So let's look at a couple of word problems. So the first one says, Joseph wants to find the side length of the square that has an area of 150 feet. Should this answer be rational or irrational? Why? Well, so he wants to find the side length of a square. What I know about a square is that all 4 of these sides are the same. I also know that if the area is 150, I know area is side times side, or side squared. So I know if I take that area, 150, and say that that is equal to side squared, well, the square root of side squared and the square root of 50, so the square root of 150 will give me side. So, will this side be rational or irrational? Well, we know that the side is the square root of 150. And again, we're looking at square root. So now we have to determine if that number is rational or irrational. So we know when we see square roots that our question is, well, is this a perfect square or a non-perfect square? Let me think about it. I know 12 squared is 144. And I know 13 squared is 169. And those are your two whole numbers. 150 fits in between them. And there's no number between 12 and 13. So it's going to be a non-perfect square. So we could leave our work as our reasoning and just then say no. Because the square root of 150 that we came up with is irrational. And the work we showed if we were to go out and say, well, to find the side length, we'd have to take the square root, which is what we did. And the square root of 150 is rational because it's a non-perfect square. Non-perfect. All right. So number 2, which values from the following numbers of list is not a rational number? Well, this first one, is this a rational number? Yes, it's a terminating decimal. How about this one? Is this a perfect square? Is this a rational number? Yes, because it can be written as a fraction. Those are two traits of our rational and irrational numbers. How about the square root of 25? Is that a rational number? Sure is, because we know 5 times 5 is going to give me 25. So 5 is the square root of 25. How about 0.321 repeating? Yeah, we know rational numbers can be repeating numbers because we know 321 thousandths. There are 3 numbers that are repeating, so 9, 9, 9 can be written as a fraction, so it's rational. And then I see the square root of 30. So my last question is, well, is it a perfect square? Because if it is, it's rational, but if it isn't, it's not. And it is not a perfect square. So the square root of 30 is not a rational number, which means it's irrational because it can only be one or the other. That was the other thing I saw in a lot of this work. You said that it was both. It is always going to be real, but it cannot both be irrational and rational. The square root of 30 is our non-rational. It's irrational because it's not a perfect square. Awesome. All right, so let's look at a couple more. So then I have Brad converted 5/11ths to a decimal, and his result was a repeating decimal. Does this mean that his value is rational or irrational? This right here. A repeating decimal is rational or irrational? You're so right, because it can be written as a repeating decimal, which turns into the fraction of 5/11. So you can say it can be turned into a fraction, or it's a repeating decimal. Repeating decimals can be written as fractions. So yes, this is rational because repeating decimals can be written as a fraction. All right, so now it gives us a couple more values. And if you look, they're all super similar. They all have 3.4567, but they have some different stuff. So look at these and tell me what you think you see that makes the 3 of these different. Well, this one, I see a repeating bar. This one, I see our ellipse or our dot, dot, dot. And that first one just ends. Well, this is a terminating decimal. What do we know about terminating decimals? Terminating. If I could spell, I'd probably teach something that wasn't math. But I spelled it right. Terminating decimal. All right. So terminating decimals ends, which means I could write that as 4,567 over tenths, hundredths, thousandths over 10,000. 10,000. So it can be written as a fraction. It's a terminating decimal, so it's rational. These dots, what do these tell me? That's right. This 3.4567 is going to continue on in some random order that we cannot decide. So it's a non-terminating. And we know non-terminating numbers are irrational. Awesome. So now this next one I see 3.4567 with the 7 repeating. Is that rational or is that irrational? That's exactly right. Because repeating digits can still be put into fraction form. This is going to be rational. Because repeating digits are rational. All right, let's go ahead. I think I have 2 more. So state whether the given values are rational or irrational. Again, they're all just slightly different. So this first one, I see 6 plus the square root of 30. Well, I can't add 6 to the square root of 30 until I've pulled it out of that square root sign. What's the square root of 30? Is it a single number? No. So what you're telling me is this is a non-perfect square? What do we know about non-perfect squares? That's right, they are irrational. How about this next one? I still see 6 plus 30, but this time the 6 is in the square root. So before I pull out the square root, I got to add them together. So I have the square root of 36. Is that a perfect square? Yeah, 6 times 6 gives me 36. So that's rational. This next one, before I can add the square root of 6 and the square root of 30, I have to pull them out. But can I pull them out nicely as the square root of 6 and the square root of 30? Are those perfect squares? No. So we're going to go ahead and say that those are irrational because they are non-perfect, just like A had the square root of 30. We can't add them until we figure out what they are. What they are is irrational. You get 2 irrational numbers, and you got an even bigger mess. All right, so then you have to give an example of a rational number greater than 10. So, let's think. I know 10, the square root of 100 is 10. So, what's bigger than, and I know the square root of 11, or 121 is 11. So 10 and 11. I know that non-perfect squares are irrational, right? So let's pick a non-perfect square between the two of those because it's greater than 11 and less than, or it's greater than 10 and less than 11, right? Yes. So I could say 110. I could say anything. I could say anything between 101 and 121. So if I said the square root of 101 and all the way to the square root of 120, any of those are going to be non-perfect squares that we learned when we were estimating, and that was one of the things you guys rocked out with those organization tables. We know that we could estimate it, know that it's above 10, and we could round it to that decimal because you guys rocked at that. But it's not going to give me a perfect square. So let's say 110, because that fits the bill, doesn't it? And not just 110, but the square root of 110, because 110 is a rational number. But that there is an irrational number. I could also say 10.347 ... Is that bigger than 10? Is that decimal gonna repeat? It doesn't have any lines that show me it's repeating. It just shows me that it's gonna go on forever. Let's see what else. Let's look back at our idea of what irrational is and see if there's something else we could think of that we didn't include. Irrational numbers, non-terminating. Well, we have that. Non-repeating, we had that, and non-perfect squares. So I think that we pretty much covered it. All right, so today we were talking about the real number system. You know the difference between what a rational number is and an irrational number, and we did some practice using the definitions to look at numbers and determine whether or not they were rational or irrational. So now, at this point, you should have filled out your notes. I want you to summarize the lesson on that portion. On the bottom of there, it says summary. I want you to tell me in your own words what you learned, which should really include this objective, because what you learned was the difference between rational and irrational numbers. So in your own words, tell me what that difference is. If you feel really comfortable with this, you can go ahead. The work on this is on Schoology. If you don't feel so comfortable with it, please come to our guided practice. If you're coming to our guided practice, you should have watched this, but if you've gotten this far, you watched it. That's all I've got for you. Please come to guided practice. If you need it, definitely come to guided practice. If you're feeling real confident about it, you can do it. Otherwise, please wait till after guided practice. All right, guys, have a great day.